Okay, thank you.
Great.
So, yeah.
Yeah, just back from Scotland there yesterday, so
Uh-huh.
all went well.
Was it a
Or
business or a personal
no, it was just a holiday.
personal visit?
Yeah. No, it was
Holiday.
pretty
Oh,
good, but it took
so
me like 22, 23 hours to get back from Edinburgh to Belfast because of a
ah,
delayed ferry.
okay.
But that's it. So what's you notice the title of the live stream today is Pi
Pi
Day?
day,
Yeah, because normally Pi Day, I think in the is the what
March,
is it, the 14th of March,
March,
right?
March. Yeah,
But that's like that's US dates, right? Because you put the
yeah,
month first, then the day. But
yeah.
over in Europe, we have it the other way around.
Uh-huh.
And I don't know if you get your calculator out and you put 22 divided by 7.
Yeah,
Yeah, you know it.
that's one of the values for a pi. Yeah, I
Yeah,
mean
yeah,
the
kind of the
fractional
estimation.
value for pi is 22/7. That's correct.
So
So
hence
that's good.
this is the lesser known Pi Day. Yeah,
Oh, okay.
you know,
That's nice.
European. Let's call it the European Pi Day
European, by the way. Okay, fantastic.
yeah. So yeah, it's
So,
funny that our live stream falls on such auspicious days.
oh
You
yeah,
know, we've had a
yeah,
number of them.
yeah. I think 14 was 14th also. Oh, Christian is here, I think.
Yeah, there's Christian.
Hi, Christian. Nice to see you
Hello.
back.
Hi.
Hi.
Hello.
So it's nice to see you
So
back again. So I think pretty soon I will
just to let you
start
all know,
maybe another.
we're live anyway. So I just
Okay.
started the stream as soon as I entered. So.
Okay. Whenever you are ready, I can start the problem solving, the presentation.
Yeah, sure. Whenever,
Okay.
yeah, whenever you're ready is good with
Okay.
me.
So let me get. I mean, always this will be always a ongoing thing, but I think we have resolved some of it, but it will be like that only. But I think it should work. Let me check.
Oh, great. Yeah, if you want to, you can share your screen anyway. I don't need to okay it or anything. It should just come up.
I think this is the one. Let me check.
So how did that go, Rajan? Did you what did you try and do in the end? Did you look at the
Yeah, I had to.
recommendations of it,
Yeah, I had to
or did
do a
you
lot
do
of.
the what was the other thing that the Christian suggested you do a small work out a
Yeah,
small part of it, was it?
yeah. Well,
So
so
which
I
of those
did
two
that.
did you do? Did you do
Yeah,
both or?
yeah, I did both because when I
Yeah.
was working out, I found because it was new to me, I found actually detailed thing which I think is proceeding the right direction, but there are a lot of work to be done. So um,
Cool.
let me start. We can, but uh,
There we go.
you see, okay,
Yeah.
yeah, okay. So yeah, so let me see. I think I should be able to, because I want to see both and this one. Yeah, kind of. So the idea that we did last time was how to convert from S2 to S4. So the original presentation with the higher markless, the our 2 by 2 matrix with the you know the fields, the vortex and these gradient fields, which is the original formalism, uh, is like a S2 matrix. Okay, so I converted. So we discussed that last time. So moving along, let me start. Uh, okay, slide presentation. I have to do. Be able to. Okay, so I might have to get what's coming up. Can you see the full screen now?
Yes, Rajan, we can.
Oh, the full screen.
No, not yet.
Let me see. Yeah, I think it's probably is coming up. Maybe I had See now? I don't know yet. Maybe I had to do then. I had to probably get off the screen and see. It's kind of free, but yeah. Now I can let me start the full screen. This is always a complex thing. Okay. Okay. I think it will work. You can share now. There is a problem. I'll work with the.
You must start the presentation and then share the screen. Number 2.
It's working now. Can you see?
Yeah, it's working.
Yeah. Okay. So let me start with that. So S2 Cottonian group to S4 crystal group. That's our original thing. It's a part 2. So I will just briefly review the last time. I don't want to spend too much time on it because I want to get into the problem solving, the numerical things. So we are saying the problem solving of the S2 group to S4 group. So I'm just referring to our last meeting. I think it's live stream. It's there available. So you can go through that. There are a lot of extra things there. So essentially, I don't know whether you can you see my cursor? Can you see? No.
No.
Okay. Not yet. I think we have to work with I don't know the cursor. There's a way to pull the cursor. Because yeah, can you see the cursor now? No.
Yeah.
Not yet. Can you see now? Okay. I'm trying to see. There is a also. I don't want to put that. There is a laser pointer. I probably should, but now I think I had to get off to put the laser pointer. But it's okay. I'll just work with this. Okay. So last time I had that. That is there already. The live stream. Thanks to Christopher, who is doing all these personal things. But it's already automatically doing. I think our live stream. So people can watch while we are going through this one. If somebody is watching, uh, virtually. So in any case, what we want is that S2 logistic group, and we went through this one. I don't want to go through again. The S2 logistic group to S3 logistic group to S4. So what happens is that, so this is the one I will review a little bit. That's the next screen. So what we arrived at was this logistic group. Okay. So it has 6 by 6 matrix, 6 by 6 matrix. And I was trying to, I'll briefly only explain this one. We can discuss that if you want more. But 6 by 6 matrix, when I went back, these are all fermion fields. You see that? So when we go back to the standard model and trying to pull up the data from there for all the fermions and bosons and other exotic things like graviton even, which is not proved yet. But the problem is the fermion field. If you look at that, it needs a charge. So, and also the 6 by 6 matrix doesn't comply with the particle matrix. So I kind of did a little workout. We can discuss that if I want to, but I don't want to go into too much detail, except that I cannot use the S6 matrix for the leptons. So leptons have charge, and I'll go through that. So we can analyze the leptons, and we know these are all classification schemes essentially, but it helps. So essentially all these matrices the standard model uses, mostly like SU group, anything, the group theory, essentially a classification. but it helps to find out there's something missing. We can figure out. That's how many of the scientists did, um, and that's helpful for particle physics because we are kind of assuming symmetry, and we know that is the problem. The baryon symmetry, asymmetry, things like that is a problem because we are assuming symmetry, and then finally we are saying that how do you come up with asymmetry? So, but it's useful for classification. That's another discussion altogether about the particle physics because it comes from a Noether's theorem that the fundamental aspects of symmetry. So that's what. That's why it's called symmetry group anyway. And so I try to put these values in. These are all the charge, parity. You have the spin and disparity, and what I call the switch group. That's a new thing I'm putting in. That also has parity. But when I put that value in, the S6 group doesn't comply with that. I think that's a natural thing. I think that analysis is quite useful because we are trying to find out what realistically this will bring out. The good thing about the logistics group is that it has a true false. We can use it for some other IT thing. But now I converted to the field group, what I call the field group. So the point field group, this is now. So now I can now put in our original formalism, right? So basically what I am saying is that I identify the problem. The equation of the quaternion matrix, the spinor matrix. So when I analyze the spinor, this is a spinor matrix, right? Then you get the quantum matrix, the overall charge of the particles, like leptons. We can figure out. I'll go through the next one, and so I can use that, and I can input these gradient vortex, which has to be analyzed very thoroughly. Close to 30 papers are there. I mean, after gauging and everything, we could gauge it all the way up to string matrix, things like that. So this gradient vortex, which obtained from the Helmholtz decomposition of the point field, is the most fundamental thing. And that I can identify charge, spin, parity, and everything. So what the problem is that just 36 possible particles, not all are useful, produces matrix with too many zeros. So when I put in the values, I get a lot of zero in the column or the row, and that shows that we have to reduce it, and then kind of rework it, because when you do from S6 to X4, we have to kind of rework it. So that's what I did first. What I'm showing is that solution is that we can use the S6. That's what I'm putting here. S6, we don't have to discard it, but that is useful for gravitational, electromagnetic, strong nuclear, weak nuclear, dark matter, dark energy. So you see the differentiation. The S4 I use for particle, and the S6 I can use for these fields, all these 6 aspects of the field and the dark matter, including dark matter. So that's a differentiation you can use. So that's a very useful thing I came up with, and I feel good about it. And I can still use the vortex gradient field. I know I'm going to discuss only the particle physics problem solving today. So again, we can go back to our original graphics that showed like a diffraction pattern of a perfect crystal thing. So all this can be used. So that's a good thing. So I can use this original formalism. As we remember, this is a rotational field, the rotational field, and this is the gradient field. That's a simple aspect of the original model. And so I just signify by clockwise, anti-clockwise, and negative and positive values. So it's the same thing as that, but now signs taken. So to S4. So it's a 4x4 matrix of the field group. So I convert from the logistic group to field group, and there are a lot of advantages because the logistic group says about the true false, not only true false, not false, not true, and we discussed that, and it has a lot of the extended Boolean to Quaternion type of logistics. In any case, so and this is an is like 4 by 4 matrix. You see that 1, 2, 3, 4, 1, 2, 3, 4. And with a compact notation, I say one, you can see it here more clearly. 1, 2, 3, 4, 1, 2, 3, 4. So each one of these matrix is this 2 by 2 matrix. So that's compacted to this symbol. Okay. So I'm just putting aside one thing about, I found something about quantum computers that we'll discuss later. But what I found was she's showing in the video how the the wave function. I always wondered how the wave function collapses, in the quantum computing, and that's one of the fundamental things, right? I found when I went through this is a permutation. What we are doing is a permutation. But what happens when we measure, and this may be part of the measurement problem, that when we see that, we see a collapse of the wave function, right? And that may be because these are permutation matrix. When we measure it, collapses to combinatorial resultant. So it's a very fundamental byproduct of this one, and it may explain many of the measurement problem, other things that we see. And quantum computing, why it collapses, whether wave function collapses, things like that. So it's a very useful uh, after afterthought results. Okay, so now I go back. Now I can apply it. So this matrix I developed can be used for fermion fields. So these are all fermion, and that makes sense because all these fields that I described, gradient and vortex, are connected with the fermion fields. So now I can connect it, and the fermion fields there are four. For the leptons, there are four charged fields, like electron, positron, and muon, and tau. They are all charged particles. But some of the antiparticles, I don't need to exclude, be part of this because they are not charged ones. So they are not fermionic fields. So I use this nicely, and it works very well for leptons because these are the leptons and they are the charged ones. So they fit in very well. So now I am confident I can do calculation on this. So before I do the calculation, before I input the values, I want to ensure what I have derived, the matrix that I derived from group theory is consistent with the standard model as well. But I will call it separately by name. I won't call it SU group. It's S4GUFT, which means S4, it's a 4 by 4 matrix, and it's a gauge unified field group, essentially. That's what S4GUFT means. Okay, so when I look at that, this is like a Hamiltonian. So this is very important. If you go to the standard model, you see that QFT, the quantum field theory, is an extension of the original Schrodinger equation, but the difference is that it uses something called canonical transformation. Again, this is a very detailed thing. So we convert using canonical transformation from the normal the Hamiltonian that Schrodinger equation uses to satisfy the quantum field theory. So the quantum field theory is the primary basis for this standard model. And eventually they made it to quantum chromodynamics, things like that, because quantum field theory cannot explain a lot of things. Again, I'm not going to go into details about that, and many of you know more than me about these things. But essentially, the canonical transformation plays the role for Hamiltonian for new variables. And as we know, the Hamiltonian is an observable, so it's a useful thing to verify the things. So they call it the Schrodinger equation as the first canonical form, and the quantum field theory as the second canonical form. And there are a lot of mathematics associated with that. Again, I'm not going to delve on that. As fast as possible. So I just want to explain the charge is rho. The rho, is the charge. The spin is like a pi, and the parity is like phi, and the switch state is uh, the chi factor. And we'll see that switch para extra metrics that will help. So essentially, I have summarized here in a way. Theory meaning is fundamental objects are quantum fields which are defined at all points in space-time. The QFT treats particles as excited states. This from the Wikipedia. I put all the references at the end of their underlining Wikipedia and some other. I had to rewrite some of the references I have. I have put only the Wikipedia, but I go back to the original references, some of them. And I had to change that eventually when you publish a paper, after we ensure that these are all correct. The underlying quantum fields, which are more fundamental than the particles. So the quantum field theory thinks that the underlying fields are the more important than the particles themselves. And I am very much consistently connected with that. I also feel that, yeah, the fields are the fundamental things. So the fermion fields are matter particles, electroweak boson fields, and you have the gluon field for the strong interaction. And the Higgs field phi values generally do not commute. Of course, we discussed that with Christopher and Christian last time, that the commutation is not generally, the matrices don't commute unless they have scalar values and multiplication. So in general, you can say they don't commute. They act upon a quantum state, a ket vector. So this is the ket vector we have, the spinor. So with that, I'm confident. Now I am going to apply these to the analysis of the lepton classification. I will call the classification. From the classification, we can figure out, are there some missing points? And that's the main value. We should not over reach and say, okay, it can do all the calculations. No, it can figure out the missing things, and then we have to do the Feynman diagram, the calculation, the differential equation, and all that to solve for the field. But that's a huge project. But I'm just starting to show the feasibility of this one. We know has a spin of half minus 1, and the switch state all 1. So say the electron is active, case, right? The electron is the active one. If you have a current going through a circuit, the electron is active, and in general, we think that it's like a Dirac sea of electrons, things like that. Even the quantum theory says that. The parity of +1, we know. But if you go to positron, which is an antiparticle of this electron, these are all leptonic particles. So positron antiparticle, again, it has a spin of half, but a charge of +1. And I say switch state 0 because normally they don't participate, right? The positrons in the normal situation, unless we got very high energies. The parity is -1. Of course, the antiparticles or antileptons have always parity of -1. And the particle or the leptons have always positive parity. So muon particles similarly, spin of half, they are all very similar as electron, except switch state is 0. We say a parity of +1, right? So essentially, it works like electron, but the muon, and we know it's the difference in mass and things like that. But in this case, the switch state helps because it says whether the particle is participating or not. So that's an additional matrix that's going to help in the long run. Tau part, that's my new thing from the formalism. Essentially, everything else is there, with the SU group, everything. But the switch state is the additional thing we are adding on. So I don't want to, overemphasize that, except that the main thing I am gaining using the switch gate. So tau particle is very similar one as the muon. And now I can put in these values and put in the value, and each one I calculate for the original 2x2 S2 matrix. For the electron, I have this matrix. So I can solve the matrix problem. Let's say and I get this one because for the charge, it's the gradient that matters. Okay, so when I calculate that, this is almost like identity matrix, and some of them are used like that. Of that identity matrix, it's not really identity matrix 1 0. That's usually for the spin. This is a conjugate of that. So it's not really, it's very similar to Pauli and Dirac matrices, which have all this type of thing. So this is not identity. So I want to emphasize that. So again, that has eventually gives a charge of -1. The positron, only difference is that it has a parity of -1, so it is 1 and -1. So our 2 by 2 or S2 matrix changes according to all these values that I input. So it has, we get a value of +1. So, and the muon again is just like, electron, it gives the same way, and tau also similar. When you go to spin, the spin is based on vortex fields. So we see that it is 1 over square root of 2. And when you put that, we get a spin. The spin is same with all the leptons and anti-leptons, the positron, muon, and tau. But what is the 1 by square root of 2 is the value of the eigenfield after normalization. So if we normalize, we are unitarizing, right? So we want to unitarize this one. And so when you unitarize, we unitarize that, we get 1 over square root of 2. And this comes up in many situations, and this seems to be correct. So that tells you that these values can matrix and they fit in very well. Again, parity is like a rotational invariant aspect, right? Whether, for electrons in general, you don't have the parity and and things like that. But again, when we put in the value for the parity, it's just like the spin, very similar to spin, except the values are 1 and 1. It's an identity matrix. So essentially, it's an identity matrix. Parity only says, it's identical unless something changes in the rotational aspect. Then it remains as as an identity. So that makes sense. So it should be an identity matrix which gives the value of 1. And for positron, however, the parity is -1, which means it breaks that parity aspect. So it's -1 and 1, which nobody has done that before. But as 1 for electron, it's very similar to parity, and it gives 1. So you can see nicely we can analyze this one, and the mathematical formulation of standard model, and also list of particle these values, as well as explanations of how they go about getting all the groups, things like that. I'm not going to, but actually I am demonstrating that what we have derived, and I want to verify, I want to ensure that before I publish, of course, but I feel confident that this will work. So I put in the value, and this is a classification scheme now, like I mentioned before, all the numerical. So I get a numerical computer, and this is what you see in many of the evaluations. So I put in the value, I get these values, and I can pull out the equations for that based on this one. So essentially says that all effect of all the particles playing the role you'll have a charge here. And actually, eventually, I think you can show that when the charges add together, you can get, normally it is a integral value, right, for all the fermion fields. But when you add together, you may get non-integral value like 2 by 3 or 1 over 3, things like that, which is like a quark. So actually, when they add together, they can quark. But that's the connection with Eltrobic and strong that I have not done that because there are a few other things we have to consider. And presently, I'm working separately. I'm not showing it here, and it seems to point out a new thing based on the vacuum decay, things like that, and I use it. So I come up with how the all the four things come together. Um, the false vacuum may be like a container for, I mean, just saying quark, um, you know, what do you call the plasma, quark gluon. So that's the basis for the strong interaction, and the false vacuum may provide that because it has a higher energy. Again, there are a lot more calculations to be done, and just this is like a from there. And the true vacuum may be where the leptons or the fermions and uh, you know and even the baryons, what we call baryons. So all this classification become like baryons, and then the baryons and the mesons. The mesons are the strong interaction things. The baryons are the weak interaction. So then you connect with the gauge bosons, but it's not normal bosons. There's a leak. There's a connection like a wormhole or something between the and the true vacuum, where gauge bosons can mediate the processes, and eventually you get output from both of them. And I come up with a schematic where I show that the mesons and gravitons come out of it. So that's an interesting. So everything. So you have the strong, the weak, the electromagnetic, and the gravitation all coming together. So I think that's one of the solutions for the granular unification of the fields. So essentially, we know that the fermion field is a basis for the weak interaction. It's a basis for the electromagnetic thing, electromagnetic fields that we see. So that's the observable. So this one, then what we say is that this particular matrix that we input helps to characterize fermion electromagnetic matrix fields of charged particles, leptons as well as anti-leptons. So that's what I have demonstrated here as an example. So that's something that I feel confident about, but something, again, more in-depth analysis necessary before I will publish that. But in some form, I can use that. So the key notes that we gather to go further is that quantum field theory eventually links to strings theory. That's something that I feel that that's how it comes about, but something we have to check. Problem with, but the strings theory solves some of the problems that is not able to come up with. But string theory has a problem. So, but we know that Hamiltonian operator is an automatic observable. So we have to work with that. And I think what I have done is for GUFG has this Hamiltonian in it. It built it, and that helps the observable. So that might solve the problem of string theory. And also my previous publications about physics formalism, I use gauge functions that extends this to string matrix, the 2x2 to string matrix. Another advantage. And I had to note that particle physics has a lot of advantages. I mean, there are a lot of problems, but it has advantages. But it helps to, like, hadron collider. I'm not going to detail about hadron. I'm going through now hadrons, because mesons are also hadrons and baryons are hadrons. So they are coming together in the classification. They come together in some form. So the LHC, large hadron collider, and everything, is able to verify some of these standard model things, right, including a Higgs boson, things like that. That we believe is what's is correct. But gravity is a problem. So in quantum field theory, that's one of the main problems. So We have to come up with the quantum gravity, loop gravity, supersymmetry, modified. This is what I used for the transforms. It's kind of like modified Newtonian dynamics, and it has produced a lot of results that the universe is like a black box, things like that. Then you have strings. So still we have to still figure out the kind of field with the weak electromagnetic gravitation, strong as well as energy, dark energy, and I believe S6 that I discussed. I'm not going to present in this one. And my original Absolute Genesis book also says the signal is obtained by certain operation on the noise. So what the F will. So I'm
Rajan, your mic is cutting in and out
so in
a
any
lot.
case. Oh, let me put my. Were you able to hear me so far?
Yeah, but I mean it's cutting out quite a bit. So if you can
let me
switch
change
to
my sometime I think I have to change my mic. That's a usual thing. Oops. Where is the mic? Okay. So yeah, mic. Okay. So now I think I can go. Let me see. How is that now? Is it better?
I don't know. Like when you're sitting forward like that, I think we can hear you better anyway.
For me, it was much better this within the new mic.
But now,
I
have 4 different mics. You can tell me which one is the best. I'll start from the beginning. Is it good? This is the first one.
There's no need to start from the beginning. It sounds okay, yeah, but yeah. Just continue.
How about now?
Off. Yeah, it's fine.
Okay. Okay. All right. So essentially, so the F in this case, again, I'm not going to go confident.
Oh, Rajan, that's
not what I published.
Rajan, it's still cutting out. If you, usually when you're sitting forward and you're changing the mic, it's.
Let me go back. Oh, how about now?
No. Well, just listen to me. When you're
how about now?
Just listen to what I have to say. When you sit forward and you're trying to fix the mic, your mic works perfectly fine. So just do that. When you sit forward.
Okay. Is it better?
No.
Yeah. Like that?
Yeah. Okay. It seems to work better when you're sitting up.
Now it's better. Oh, yeah. Okay. Thank you. Thank you, Christopher. Yeah. Thank you for pointing it out. Because only you will know. I don't know.
Yeah, it works much better. Yeah.
Thank you. It's better? Much better? Okay. Thank you. Yeah. Okay. So it acts like a filter and function is both as a filter. Those are the filter, and then you.
Sorry.
How about? Can you hear? It's okay. Okay. Synthesizer will have
every time we start. So just keep going.
Is it okay?
Okay.
Yeah, okay. I can probably change the.
Yeah, do. Yeah, just change it one more time. See if that works. And then if not, we can kind of. How many more slides do you have left?
You must speak in the direction of the microphone and not to the screen.
Almost.
I think the microphone is on his head, though, Gert. Is the mic on your?
Yeah, but also I have on the screen.
Why do you have 4 microphones? I don't understand.
My
because I have one
at the screen.
Yeah.
Yeah, there's one on the laptop.
Yeah. Yeah, use that one. Use the one on the laptop then. Maybe.
This is good. This is good.
No, it's not good.
Better?
No. No.
Is it better?
Yeah, that sounds the best.
Yeah, for me as well.
Is it the best?
Fine.
That's the best one?
I think so, yes, the loudest.
Okay, I will do one more.
Okay. This one has slightly less interference, I think.
You can also
Now I don't hear anything anymore.
is it good?
Yeah. It's okay.
I'll
Pretty good.
now.
No, it's cutting out a lot though. I don't know what the problem is with your microphone setup there, Rajan. You're going to have to work on that. So
I know.
It's been a problem over the last
maybe the
couple of live stream things. So definitely test that out before you come on next time.
How about now?
Yeah, that's probably the best one.
Yeah. I'll put the noise reduce background noise. Maybe it will help.
Okay. Yeah. So how many slides?
I don't know whether it's helping or not. But
yeah, it sounds good. So
it's almost ending.
You're nearly at the end. Okay, so just keep going then, and then
it's almost the end. Yeah,
great.
you're very near. Yeah.
Yeah, that's much better.
They only like this may be one of the last ones, and then I'll just show. Okay. So this is the one I will discuss later about how the signal is produced from the noise. But essentially, I just want to point out the synthesizer functional. So the F has different purposes, and that's essentially of that. Eventually, I can make into SN logistical group to SN the field group, just like what they do special unitary group. Eventually, I had to find a correlation between this the field group I have with the special unitary group. That's probably much later, but I think that's what we have to come into. And this is showing promise that that essentially this is working for leptons. Now I want to expand that to S6 logistic group. So what is happening is that S6 logistic group collapses to S2 logistic group. The S6 has permutation aspects, whereas the S2 logistic is a combinatorial aspect. So it's like lock and key. So this will explain why the wave function can collapse, because if we have all this stuff, all the 6 fields, like I mentioned, the gravitational, electromagnetic, strong nuclear, weak nuclear, dark matter, and dark energy, if I have that, they'll all collapse to our S2 logistic group, which contains essentially the fermion thing, right? So essentially, what we see is the fermion thing. We don't see the strong interaction in our normal lives. So this is the interaction process. We'll have, but this is important to characterize, right? Because we don't know still dark matter, dark energy. So this matrix, that S6 can pull up that matrix, and we can include the additional aspect of flavor and color, right? Because in order to describe the strong interaction, we need the color, because quark has color charge, and the gluon essentially is the mediator. There's a big difference, right? Because in the case of fermions, from the Feynman diagram, we can see that only they are mediating it. But in the case of strong interaction, not only they mediate, but also they participate. The gluon participates in the process in addition to mediating it. So the color charge has a lot of things, and I think Christopher has done a lot on that, and we discussed that. But I'm touching upon that. So the S6 can do include that and include the strong interaction. Thereby, I get the metrics classification of the metrics of the strong interaction. So this is for the strong nuclear metrics. We can do that. So gluons themselves carry the color charge, mediating exchange force among quarks. And usually the emergent has a different color than the entering color, things like that. So you have the RGB things that come in the picture. Participate in the strong interaction. This is where quantum chromodynamics is coming into picture. The QCD comes into picture. That unlike the photon mediating electromagnetic interaction without electric charge, right? the photons don't have mediating it. Then I can extend to S8 to include exotic fields such as the torsional that Christopher and myself, we have been talking about that, the torsional aspects. And I believe the torsional aspects comes gauge boson. It might not come in the normal photons, the bosons that are normal photons, but it may come the torsion in the gauge bosons and the other such as the bosons like the gravitons, things like that. The torsional aspects will come. And Sakarango waves. Sakarango is the person that in Canadian Journal of Pure and Applied Sciences that we are publishing. He's the editor there, and so they have done a lot on this one. So again, the coupling aspects come there, the gauge aspects come into the picture. So the coupling is, they have done a lot of evaluation. There are a lot of values for the coupling, and we know that the Yukawa coupling and all that, and probably the Yang-Mills problem. I don't know. With this coupling and gauge and the flavor color, maybe we can start looking into the Yang-Mills problem. But again, I am not sure whether that will have solution to that. Oops. Why is it not responding? Oh, okay. So these are references. Again, you can go through that. Like last week, I extended that. And these are some of my publications. Not all of them are here, but so this will help to understand the strong gravity. These are the new papers that are coming out. Some of them will come out only in October. The two of them are already there. I think you may have seen in the ResearchGate. And but the other two contain very important things as well, analyzing of switches, things like that. And very interesting thing. Again, I'm not going to present today, but I can express the off state in terms of a quaternion of the on state. And we can actually use nicely that if we put on equal to 1, that's normally used, then we get value of the off. And we don't have to worry about C square equal to 1, things like that. We don't have to use that. So those are some advantages. So algorithm, which is already there, and this continuum that I'm working with Emery, and we are advancing like 8th paper almost, and it shows a lot of new things. And then I have some of the literature survey I have done. Some of them I am putting it is how to convert S2 to S4. It's there in the forum. Matrix multiplication, commutative or not, it shows, and the S2 is abelian, and there is a proof for that. And then Higgs discovery, the power of empty space. Then fermions, quarks, and leptons, polymatrices, and they are the fundamental things, right? The Dirac matrices, parity physics. There is a whole lot of physics on parity, comes into picture. And I think one of the persons like Carl Bender, people like that, have looked into detailed analysis of that. Second order tensor, boson, graviton is called a spin to second order tensor boson, things like that. And graviton, they have not been able to verify yet. The spin charge antiparticle mediated mass values, fermion, boson, quarks, leptons, and hypothetical particles like gravitons, superpartner particles, composite particles like hadrons, baryons, and mesons. And in that one, they say magnetic monopole is a generic term for non-zero magnetic charge. So some GUTs, grand unified theories, are predicting that monopoles had to be there. So these are all literature things that I pulled out. Then this book contains group theory application quantum mechanics. It's a very useful one. Symmetry groups S4 and Cayley table. I think Christopher might have used it quite a lot, the Cayley table, and he's analyzing with his complete geometric group theory. Electron classifications, again, why they don't undergo strong interaction. There is a lot of literature on that. What is parity? Then polymat spin matrices, strong mediator gluons exchanging force between. Again, they give you some graphics of the color charge works. Then you have mathematical formulation. That's a fundamental basic thing of the standard model. Then weak interaction, direct matrices, Lorentz sinners. Then you have the how I was asking it how the QFT is connected with Schrodinger equation. I showed you that research. Will gluon produced by electron positron mediate by the photon lead to strong interaction? So the gluon is produced, right, from the Feynman diagram of the electron positron mediate by the photon. The gluon can be produced from there. Can they participate in strong interaction? So again, there are some literature which says that it's possible, and otherwise it's not very clear. The gluon Wikipedia, the gluon itself. Then our own Livestream, which has all other things, all the previous. So this is essentially what it is.
Okay, great.
I will entertain. Thank you very much.
Well, yeah, just
listening
before anyone
so carefully.
says anything else, I'd just like to say, however you,
so
whatever setting your microphone is on now is the best. So use that from now on, is what I'm saying.
Okay, thank you.
So just make sure you remember what that is, and then
let me check which one it is.
Okay.
Yeah,
make a note of
that. Yeah, that's the second one. Is showing communication mic in front at the front panel, real tech. Okay.
Front panel.
It's a black.
Do you have a desktop? Do you or a laptop?
Communication. Yeah, it's a communication mic.
Okay.
Yeah, it's a laptop. So, yeah, communication. Yeah.
Okay. Right.
Okay.
So yeah. Okay. So I mean, there's quite a bit there. It seems like you've changed stuff from the last time because it didn't work. And that makes sense.
Yeah.
To do that, obviously. I didn't see your justification for S2 and quaternions, but I don't know. I think you did a lot of work anyway. And it's a complicated field of research. I'm a bit confused about why you're doing electron, positron, tau, and muon though, because what about the anti-tau and the anti-muon? There doesn't seem to be a symmetry there. You're saying that those are the only ones with charges. How do you justify that? Surely the anti-muon has a charge and the anti-tau. I think you're thinking you might be getting mixed up.
The reason is that I'm looking at the fermion field.
Can you wait? I think you might be getting mixed up between
no. What?
No. Okay, sorry. Go on.
No. Let me explain. The reason is that I'm analyzing fermion fields, which should have a charge. If they don't have a charge, I cannot put in there because the original model uses charge. They have to have a charge in them because it's a fermion field. So
are you saying that anti-muons don't have a charge, or what?
No, they don't have. Anti-tau don't have a charge. They don't, and the anti-muon.
Where does I don't think this is correct. So from electron muon tau, anti-electron, anti-muon tau have precise measure to the 21th digit the exact same charge, which is the electron charge numerically.
Yeah.
All these particles have different mass, but they have the exact same charge. Of course, the charges have a sign, and let's say the quarks, which gets us to the living humans that we can think and talk and discuss like that, are just the U and the D quarks, but the others are reliably, really reliably measured in accelerator experiments like in CERN and thousands other situations. And this is beyond any doubt, Rajan, that the charge in leptons is identical, without any doubt. But maybe I misunderstand the core thing. I was wondering, because you had a 4x4 matrix, and I would have, from what you said, expected that you talk about this 2x3 matrix or another related higher resolution matrix, where that is what you called the lepton row, or whatever you try to find there in the particle arena zoo, would have been a superset of that, but it cannot be a subset of that. And it can especially not be a 4-dimensional one, because there's even mathematical proof that 4-dimensional matrices have some mathematical restrictions which are proven to be incompatible with that kind of leptonic resonance.
Christian, your sound is very bad, and sound
I'm sorry, my fans are at full speed.
and picture is out of sync.
Yeah, maybe I'm sitting on my old PC here, my old Mac actually. The fans are running at 5,700 because it's very hot here.
Yeah.
And you might only hear the fans. I have no headset here with me. I'm really sorry. I just made it in time to the
yeah, no
meeting.
problem.
I can only mute my mic, then you might not hear it anymore.
Oh yeah, if you do that, we won't be able to hear you either, though. So that's not so good. Okay, so yeah, I don't know if there was a help, Rajan. I mean, I would have thought if you have these matrices, you know, like Pauli matrices, they can be 4x4. They're usually all the SL2C can be 4x4 in a sense, in the complex sense. So they could have something to do with fermions, but I think John Bayes says that a 4x4 real matrix, then when you convert the quaternion or the complex matrices into just real number 4x4 matrices, those are related to bosons somehow. I guess because they're all real and not double covered complex spins of the fermions. So you can therefore model bosons which don't have that double cover spin in with the real number matrices. But so that's kind of a lot of my work would be, well, not that it really hinges on that aspect, but it's just sort of ties on from those points of view. So I think the 4x4 matrix to describe fermions, that's fine. I mean, I think there's an issue with S4. I mean, how many elements are in S4, Rajan? There's any idea? Rajan?
Okay, let me. I'm trying to pull up.
Well, it's a quick answer.
Standard model. Oh,
how many elements are in S4? Because it seemed like you.
Oh,
I'm confused about it. You didn't show any of those, or
I have 4. It's a 4x4.
No, there's
the 4
no.
four particles.
It's 24 in S4. 24 permutations, yeah? I think you're getting mixed up with S2 and
24
S4.
permutation, yes.
Right. Okay, so what?
Yeah, there is.
And how many generators?
4x4.
How many generators in S4? You could use generators maybe, but you can't use... There's 6 generators, isn't there? Anyway, yeah. So these are basic things. You can't really. I think you need to know these things before you start discussing them. Maybe I think that the issue is, you mentioned it in your email to me, that you're kind of working in a very theoretical manner, and then you're looking at the literature to see if you're right. You should be doing it the other way around. I think you should look at the literature and base your stuff off that. Maybe it might be.
I do.
It'd be less of a like shot in the dark as to what's going on.
I do a trial and error.
Yeah. I know you've done a lot of research as well, but yeah. So, and that's good, but you know, I think maybe it might be a little bit hurried. I've made all these mistakes as well in the past. I tried to map S4 onto the bloody, what's it called, the full octahedral group. And that was a complete waste of time. Well, it wasn't a total waste of time, but it was. It's not possible. So stuff like that, you know, when you start off, you make these stupid mistakes. But the thing is, I think you should be a bit more prepared, maybe, but for if you're gonna, because like one thing about publications in journals. But what we're trying to do here is like, this is equivalent to a publication in a journal. You know, so then we're just going to, what we should do is just critique this, like peer review it then live and say like reject or accept. And in that case, I would just, I would say reject. with you know, but like that's if we're looking at this as a publication thing, which you obviously weren't, so I don't think it's fair to do that to you this time around. But in future, I would say even if you're going to do like something very theoretical like this, maybe write a proposal first and then send it to us, and then we'll go, yeah, this is good enough to publish, which is what we're doing now, or not.
Yeah. I
We
don't
don't have to
publish now.
reject
I'm
it.
not going to
You don't
publish
have to
now.
reject it on a live stream. We can just do it in an email, and then, you know. But I appreciate that you've done all this work and that you've taken the time to present it. But I think in future that's the way we should go. What do you think?
See, so let me point out something about the charge.
Okay.
The electron has that, right? Electron neutrino does not have a charge. You see that? The muon has a charge. Muon neutrino has don't have a charge.
Electron neutrino. Yeah, but that's different to a positron, and it's different to a muon. You see,
the muon.
You see what I mean? You were saying there's also anti-muons which have a charge, and then hang on, that doesn't seem. Yeah, anti-muon would have a positive charge,
it's
and the
half of the table actually you need, and even then. We don't know what the full table would look like from a physical aspect. I think from a charged particles point of view, the quark model is just that, a model, but a well-working one theoretically for the last 40 years.
Yeah.
And personally, I don't like it because it never really fits to I-space beyond 4 digits. So when I try to calculate muon masses and that stuff, I can do that. Actually, it was very hard. Very, very hard, and I can do that, but I never get better than 4 digits. Now that leaves for me, for example, for I-space theory, 2 options. Either I-space theory is not suitable or completely wrong with respect to monic leptonic theories, or they are just a harsh approximation for space-time reasoning we don't understand yet. And I tend to hope for the second, put it this way. But the matrix itself doesn't go away, Rajan. It is just you're playing with the charge fields, with the spin fields, with the vector of a half, and so on, the numeric value of a half. But what I have been lacking from the discussion we have had 2 weeks ago, I think we met last time, right? Right, 2 weeks ago it was. I also had a problem to send you the email of the example, which I would wish. So I do not criticize that there was not really more in-depth an example of a single row of your equations, but I will send you really, not today evening, but tomorrow. I have it because I had problems with my Macs and PCs in the last week. It was a very busy week. I had no time to even prepare anything for today. I'm really sorry also. So I'm naked in a sense today here in the last minute into the meeting.
Fair enough.
But nevertheless, I had hoped a little bit more on not repeating what you told us in a bigger depth. So this is the feeling I have. You repeated what you showed last 1.5 hours in more depth, which is surely good to focus better on what you wanted to say. But what I'm still lacking is a single line of example in full depth detail, and not about the values of 1 and a half 1. For example, you're saying, I think, I don't remember the page, that the momentum is 1 over the root of 2, which is true in some unit systems. But as such, if you don't explain what unit system you use, what kind of basic assumptions you have, what is your speed of light? Number 1 is your speed of light. So you're not telling us anything of these kind of details, and that are required details to discuss with you. We cannot interact with you on abstract matrix information. We are not mathematicians. At least I'm not. I cannot follow these things if I don't get guidance in what we are talking about.
Right. I thought the 1 over 2 square root of 2, is that not to do with spin?
Yeah, it's Har-bar over root of 2 or something like that. And Har-bar is fully dependent to the measurement system or unit system you define it in. And if you're in a SI system is something else, then an I-space IQ or I-space SI. So
yeah,
it's
well,
covered by the fish. This is what I wanted to say. Like in this table on the right side, you see the mass, and the mass here is in electron volt. mega electron volt per c squared, and that is objective. This is things which I can understand. Now, when someone makes a table like that in Wikipedia, is it Wikipedia? I don't know. Then I want to see how the hell from the 4 left symbol antiparticle spin charge you come to the mass on the right side. And I bet my ass this table has not calculated the mass on the right side like I
No, I didn't. I don't calculate the mass.
measurement value because they cannot calculate that.
Yeah.
And that's the thing. But in your theory, your mapping is the best word I can find. Particle or geometric space-time objects to simple matrices, in the sense not simple for the sake of a nested matrix of a very high order, but nevertheless based on integer values or small combination of integer values like a third or a half or the root of 2, coming from the physical routing of these values. But this is not enough to get the grip on how the particles would form from that, because if it would be that simple, Rajan, a lot of people would have found that in string theory before. It is not that simple. There are a symmetry and a symmetry group there, but we haven't found them yet, and it's good to discuss these things. But then we need more to know what is in your brain about where you come from and where you want to go to. It looks like a snapshot in between of your, hey, I have the thought of the week, and then we discuss the thought of the week, and it's all good, because I believe discussing things without being criticized too harsh is exactly what we want to do here. But we need to have the basics to understand you. I cannot understand you this way. I don't know what you had thought before, and I'm especially not seeing the direction where that we go to. And when there are formal mistakes, like Christopher said in the period, it was exactly the same question I would have had. On one of the pages you showed where the matrix was a 4x4, and you said the 4 generations of electron, positron, muon, and tau, I believe to remember. And that is just a wrong matrix. There is no electron, positron, muon, tau table anywhere in physics. There's electron, muon, tau, anti-electron, anti-muon, anti-tau. That is the table.
Yeah, actually the S6, this is just I'm not showing this is the final solution or anything. This is just a way to get to the, there are a lot of calculations we have to do, like from the Feynman diagram, and then we have to actually calculate the field values and things like that. And that's where the mass and everything will come into picture. I'm not calculating that. This is just a very, very preliminary thing. I'm not saying this is the final thing.
Yeah, no, we understand that. I think that's perfectly understood. But we're saying that even in this like beginning, there's a lot of errors, and so you cannot talk about going on to do anything with this, because what's there is just not there yet.
Yeah, no, but S6,
you need to spend time. I would suggest write a proposal next time or something, but don't stop presenting or anything. I think what could be interesting is if you were to, how you like spend time watching Sabine Hossenfelder's work. She kind of like looks at what's going on in science, like what are the big developments, and then reports on those and gives her opinion. So maybe I think if you could do something like that, even every week or something, just for like 10 minutes or something, this is happening, this is important, we should pay attention to this. Something like that would be very useful. And then when your bigger, broader research gets off the ground and you're like, yeah, I know where this is going now, we're going this direction, then by all means. But I think until then, it's just a little bit too, I don't know how to say this properly, but it's like watching something forming that isn't quite sure what it is yet. So it's kind of, it'd be better if we knew, like, okay, it's formed now and this is it and this is the direction it's going. That would be more helpful to me anyway. So what I prefer if you did would be to look at, for instance, there's a guy who wrote a paper there, I've forgotten his name. He wrote a paper and discovered that the universe is now, they think it might be twice as old as they used to think it was. So 13.8 billion years or whatever.
I think Gerd also find that, right? Gerd also is finding very similar thing.
Did Gerd mention that?
I think
well, maybe.
maybe
Well,
older.
I mean, this is it. I mean, but
Emmanuel has analyzed, and he said that it should be larger size, things like that. Yeah.
Well, I mean, the universe is potentially infinite, but yeah. So yeah, but the age of the universe, that's an odd one. I mean, we've had 13.8 billion years, and that was kind of fairly set in stone, and because of the Big Bang model. Then we have this, what is it, the James Webb Telescope, and its most recent observations of very distant galaxies, and all of this stuff to do with
this is
like
all
the age of
interpretation.
the universe. Seems like
there's no real new paper out who in any way proves or even indicates that the universe would be twice as old. There is new measurement out from an ultra precise measurement of the Hubble constant, which shows it's about 71.994 somethings, yeah, slightly microscopically small above the one calculated by Gert's second preference and my first or the only one, which I can do with ice-based theory. And that is interesting because it shows there are two different schools in calculating the Hubble constant. They are not wrong. They are just doing the best in their framework to get incompatible values where all groups don't understand why that is. But when you look into cosmological distances, and I found a very interesting paper yesterday, which I discussed internally with Emmanuel a bit. I forwarded it also to you, I think. I'm not sure if you have time to have a read in it.
No.
And it's from a guy, Professor Whittaker, which he wrote in 1903 and 04, so 100 years ago.
Oh, yeah. You did send that on to me, yeah.
More or less 99.5% that of the ideas of what Emmanuel is doing at the moment with longitudinal superluminal waves in ether, and I was really shocked to read that 120 years ago. Really, that was just a full hit in the where you hit completely on the bee stalk, and all bees fly out and said, "Wow, now you found it finally." So the guys of this age have been, like we do, harshly discussing different incompatible models with each other. And at some point in time, mainly the Solvay conference, it was settled by definition. And it was settled by nodding people like Einstein is right and everyone else is wrong, because we need to stop discussion and get on with physics. While I understand that is a political solution and not a technical one, and I more than ever now hardly believe we have to find a way to get an experimental proof for either. And then all of this discussion will be over within milliseconds.
Hang on a sec. I mean, I don't know.
Scientists on ResearchGate who heavily research, as an Australian physicist, a female one, don't remember the name, and another one who are doing with their own funding and everything, but really professional ether-wise detection to falsify the Michelson-Morley experiment. And I have read a lot in the background information of theoretical papers in ResearchGate, which I just get proposed by the ResearchGate team. And this is a thing in its own. So the ResearchGate team, I'm not sure how that works for you, but the demon the AI who proposes papers to me to read is nearly 100 of 100. I have not a single time been proposed a paper to me which was a waste of time to even look at the title or the header or what. Always when I did look, I cannot look at all of them, but when I did look, it's 100% match to what I want to read. It's sheer unbelievable. So that ResearchGate is heaven sent AI for free. Really, I cannot. It's like having an assistant walking through thousands and after thousands of papers and proposing the best for my interests. I can only hope this is the same for you.
Yeah, it is quite good. I mean, I don't get like you. I probably don't have as much time to read as many as I would like, but so that is an issue. I haven't really been. I do get some stuff that I don't know why I'm reading it, but it's still very entertaining and interesting. But it's not like.
It depends on how much people you blocked in the beginning of ResearchGate. I'm long on ResearchGate now, for 12 years, I think, and it was participating them from the nearly beginning. And
but you block people on ResearchGate?
You could have blocked people when they spam you. You block them, and in the beginning it was flame wars between these kind of people in discussion groups. And the new algorithm is much more smart. There's a lot of been written in on the guy who also did the what is his name? Who is doing the physical crusade on the abolishment of everything which is not integer. at Gerg. Yeah. So on at Gerg's blog, they discussed a lot about should we completely abolish quantum mechanics by doing integer calculations only, and having his way of math. And of course, people were heavily discussing with him in a very unfriendly way.
Yeah.
So he was intensely talking to the owners of ResearchGate on how to get productive again by having a way to block people without them knowing they're being blocked. Otherwise, they get pissed off and create new accounts and all that kind of fake accounts. And that has become dramatically better. So there was a cleanup area about 5 years ago where ResearchGate when all that nonsense. So they did an AI or something, and I stopped from one day to another. So the newest algorithm, what I perceive is, I have no idea if that is really the truth. This is what I perceive is, you don't get your own articles anymore. So if you look, when you get promoted or recommended or something like that, you can't read your own recommendations anymore because you filter you out from your own stream. They just show you the other ones. And you would need a minimum of 2 totally independent accounts to cross-check what is actually really discussed. So when a person is heavily attacked on one discussion thread, which is public, like our video here, it would happen that for the future on, when the attacked person or enough person blocks this guy, he's silently faded out by thinking the discussion has stopped, but the discussion is fully going on just without him. This is extremely smart.
Yeah, that is good. That is weird, though. I had no idea any of that was going on. I hope I haven't been blocked from the site somehow without even noticing. That'd be
no,
funny.
you're too friendly. Well, the people like me would get blocked by shooting into that. But yeah, so
cool.
I'm not thinking friendliness is always the best kind thing.
No,
this collaboration is good, but in science, hard critics must be possible. And if you're not able to face hard critics, then I think nobody is urged to go on a stage and be public.
Yeah, I also think there's something like, you know, when you start really criticizing someone, it means that you respect them. You know, you're like,
absolutely. I owe time to the person to think about it and give feedback. Is the biggest respect one actually can give is giving time for feedback.
Yeah. But I know it can be difficult. It can be definitely difficult if you're, especially if you're new and you're like, oh.
Yeah, that can be harsh. Absolutely, yeah.
Yeah. Sorry, but I cannot say anything because I didn't understand because of the bad sound quality. But I want to say that I calculated 2 values for the Hubble parameter, and the second is 68 point. A lot of. We will see why there are 2 different values. I cannot say because I don't know.
If you're allowed to interrupt, Gerd, I believe you're the only person in the world who can say. Because you have 2 values.
Yeah.
All the others have only one in this theory, and you're the only person, like a Rosetta Stone kind event in the universe history, that has both values and both correct values. So when we have the I-space representation of the one value, which gives 68, and the I-space representation of the value which gives my value, just with different geometry, then we are mathematically able to see what geometric factors give the difference between the 68 value and the 72 value. And I'm actually wanting to do that for 6 months now. I'm really sorry that I wasn't able to do that yet, but trust me, we will do that. And that means we will have a geometric, integer, exact mathematical factor to show what is the difference between the maximum of n's of Hubble constants. And one of the things which I was reading in the last month in background only was that, and that is really interesting, by the way, and you can tell me later, please, if you knew that, because I didn't knew that. It is experimentally and theoretically verified that in the infants of the universe, so when you look 500 million years after the Big Bang, whether the Big Bang now was or not aside, okay, so about 12.5 billion years ago, roughly, all measurements of the speed of light were about 20% slower. 20%, not 2%, not 0 to 2%, 20%. And that is for a simple reason. The universe was smaller if you have a Big Bang. When there is more mass per cubic volume, you get attraction and you get much more gradients, and the speed of light slows down by a factor of 20%. Sorry, bullshit. What do I tell? The time slows down by a factor of 20% while the speed of light is constant. But as speed of light is meters per second, your distances are off by 20%. Now, when you don't compensate for such factors in your theoretical thinking, when you compare quasar explosions in 12 billion years to quasar explosion in 6 billion years, should they exist, I don't know, just as an example, then the quasar explosions will give total different resonance and timing values, because you haven't accounted for that the time was ticking much, much slower over the whole existing universe at that time of the universe. I mean, this is a thing which I would have completely overlooked. I have found a quantum of time, okay? And the quantum of time is not relativistic, which means it is part of the subspace time, for sure. So it is part of the time governing the rules and activities inside subspace, what I define 6-dimensional or 7-dimensional subspace to form the constants of nature as they are, and as I can calculate them. But when you use the atoms as a whole in a space-time which is Euclidean or non-Euclidean, hypergeometric, bend, whatever you like, Einsteinian style, then you need to calculate the distance relativistic. But nevertheless, if you're not compensating for any factors of the age of the universe, and why would you do that in a normal, when you measure atomic precision, you measure them in an Earth-bound environment in space. Yeah, like the satellite is going 50,000 kilometers over some place with atomic clocks, and you measure to 12 precise atomic digits that everything is fine, but this is completely meaningless from a universe point of view, because we have no satellites out there in Alpha Centauri or in the next galaxy, and can quickly ask them what the time would be, would they measuring the same physics there. It is Einstein's assumption that the physics is all over the same. And all our local equations and corrections which are necessary for GPS, unfortunately, show that some of the theories are completely wrong. Otherwise, they wouldn't need that corrections.
Well, wait a second.
GPS needs corrections in way more than they have initially thought to keep them in sync, because the clocks get much better than their theories could give.
Yeah, but it's the clocks, because the two values comes from one calculation or measurement is by the background radiation, and the second one comes from astronomical observations, and it may be that the background radiation does not
take into account,
carry out the whole world radius, because it doesn't strive the edge of the universe, and the way is a little bit shorter than from the astronomical observations of the first celestial bodies.
Yeah, I think we should wait until we did the I-space calculation with your equations, and then we have not only numerical values, but as usual in I-space, numerical values are unique, and unique values can be assigned unique units. Like when I see the 6961, I now know I need to take it 1 over 6961 and append I-space seconds. When I see golden ratio, I know now that I need to append ampere and I-space ampere, which is coincidentally the same in two different unit systems, like in SI and I-space SI. But doing it this way, you get a factor, and it's physical understanding where the factor not only geometrically and algebra-wise comes from, but physically.
Yeah, but I think your 71.99 will be cancelled out by the latest JST observations. and a value of 68 point a little bit is better because there is a greater age.
See, this is what I don't believe. There is no greater age of the universe. And either the whole Big Bang theory is wrong, and then all assumption that you run a theory with continuous curves from a point after the Big Bang is completely moot. Agreed? This is an assumption that there was a Big Bang, and without Big Bang, all of Gert's theory is gone, and even most of my theory is gone.
There is only one age, but I calculated age by measurements of microscopic elementary particles, not by the universe.
I'm not saying right or wrong yet. What I'm saying is, let's check. And what I'm also saying is extrapolating over the large in the sense of cosmology is a gambling which I wouldn't do too much these days. And extrapolating over quantum mechanics was a gamble if you extrapolate below 10 to the power of minus 13 meters. Quantum mechanics is perfectly right, even with ice-space compliance, to 10 to the power of minus 13 meters, and then it's completely off because the geometry changes in ice-space from Euclidean pi to pi is 3. And after that, everything is completely justified by ice-space theory because ice-space theory can calculate constants of nature and all other theories can. And as I don't think this is an accident, we have a symmetry breaking there at this edge. And I find a lot of theories which calculate with exactly 10 to the power of minus 13 meters as a border of something which they are not qualifying further, where I can qualify it exactly.
Yes, it's a gambling, but I calculated some values with about 10 to the power of minus 10 or more. And that's no gambling.
This is the wonder of your calculations. But nevertheless, the input values have been measurement values, and the measurement values have been very precisely calibrated by the Kodata committee. And this calibration was only possible due to extremely precise physical measurements up to the 9 and 10th digits. But
I calculated it also with your values from ice-space.
And it converged, and that was the second wonder, because I actually wanted to falsify you, and then we were sitting with a beer, and I was not smiling anymore. So,
but it doesn't form the difference between. It doesn't form the difference between both Hubble parameters. The difference comes out from the shape of the electron.
Really?
Once I calculated the radius of the electron as not curved, and the second value comes from a curved value.
Okay. And let me put it this way: when Emmanuel's theory has a bulge in the perfectly round shape of the theoretical electron as Dirac had foreseen it. By the way, if you have the time to go into a cinema and watch the current film or from
Oppenheimer, is it?
From Oppenheimer, it's really brilliant.
We are seeing it today. We plan to see it today, and I will tell you next time.
Oh, great!
We can discuss.
I can only suggest you watch that, and
will do.
There's one thing I hope that anybody will read my calculation and detect the difference and find out.
I cannot do that alone. I need you to do that with me. You need to visit me some point in Neubiberg, and then we do that together, please, a whole day. And
it's in your metric universe.
Go on.
What page is it?
If I may say so, one of the comments I have is that, of course, I thank you for the feedback and I will make the correction. But two things, I just want to say two things. One of them is why I didn't include the antiparticle of muon and tau is that they normally are not there participating. So that's one of the reasons. But positron does participate. Positron and electron participate to form the quark. That's a normal quantum mechanics. So I'm just doing normal quantum. I know that it's not a complete thing, So I'm going to do the more complete thing, which includes the antiparticle of muon and tau also. And I'm going to extend that. But right now it's just a initial thing. And the second one is that, for example, the GERD and people like that. I'm not criticizing Christian or Christopher or anybody like that, but I look upon as a positive thing in the sense that I look at, from my point of view, I may be not correct even, but like GERD's presentation, when I looked at it, or Emmanuel's or anything, what I look at is that whether it is pointing to a better solution or not. This is how I evaluate, like Christians or Christophers and everything. And the reason why I formed this one, I am the CEO, right? I am final person, along with Christopher. Is that why I want to continue is that whether I look at only main point is that there may be a lot of things wrong in that, like Emmanuel's work, and we work together, and I work with Mary and that Manuel. Of course, they are not able to come here because of communication aspects, but there are a lot of, I can immediately see a lot of things like Christopher is working on, and he had to correct a lot of things. But what I see is that whether it's pointing the right direction to a solution or not, that's all I am looking at. And I feel that all of our work is pointing the right direction. Of course, we'll go to debates and things like that, that you may reject my work, I may reject your work, things like that. That's a natural thing. That's a natural consequence of the scientific process, right? Because we are criticizing, after all, the fundamental things of Einstein. In Mary Taylor, we are falsifying a lot of Einstein's work, as well as the quantum mechanics of Bohr. So we are looking at, we are saying, there are a lot of faults with that. Okay, so ourselves, we have to self-criticize, and I myself will say, I'll self-criticize and appreciate your frank statements, even on lighting, even though you are saying you are rejecting a Christian or Christopher saying rejecting. I think as a positive feedback, in the sense that I can correct it. So I see as a positive point. I am able to take it. Like John, some other people are coming on, they may not like it. If you say reject off kind, they don't want to see that. But I think since I have published some papers, I don't feel any bad, because if I go on stage, even if Higgs or Penrose goes on stage, even though they are Nobel laureate, people may still say, I'm going to reject your work. It's quite possible, right? They are Nobel laureates, they're established people, but they can still. So that's how the science works. So I am nowhere near that, nowhere near Higgs or Penrose, but I feel, if you're feeling confident about it, GERD is confident, and he has written a book, and he's able to present it, I see a positive points. And that's why I work on. I don't look at the negative aspects. I know there are a lot of negatives. There may be more negatives than positives, especially in my work also. There are a lot of negatives. But if I want to not get depressed about it and want to go engaged about it, and I have gone through this stage before, because I was highly critical, and I may not even publish one paper, or any of this will not happen.
Rajan, I completely agree with you. So the thing is, we have, with our discussions, learned a lot from each other already. So one of the things, my iSpace model, for example, never, for whatever reason, I had on the radar was the kind of ether as such. And the second was the superluminosity of within the ether. But the only thing I had seen in my equation, things which hinted me to superluminosity, I said, yeah, okay, that is probably wrong. But when you discuss with people that they have other good reasons for an ether, and they come from a totally different end, and see longitudinal waves with physical explanation why they should exist, and then you get a research feedback from a 120-year-old paper saying exactly the same thing, then that hooks me. Okay, hooks me. That is what I say. Wow. Okay. Most interesting papers I've found have started with the correct citing of extremely old historical ones, which have been traditionally completely overlooked by mainstream science. And it's not our job to parrot what mainstream science is saying.
Yeah.
That doesn't say that mainstream science is always wrong.
No,
not
that's
true.
true.
What is a forum which allows us to think freely. And in the sense, I created Project 42 35 years ago for the IT, basically. where I allowed myself to have discussions like that. So please, I can be very harsh in my critiques, and I'm still very sorry for that what John was reflecting negative out of what I said, possibly, or not said, or that was not ever meant by me to be a critic. I saw that his kind of magnet theory, fridge kitchen magnet style, cannot work, and this is what I told him.
Yeah, I think what's your opinion there, Christian? I know. I'm just saying. I don't know. I respect John. John has a total worldview, a total view of the universe. Not saying that he's right, but it is what it is. It's very, at least it's consistent, self-consistent. So, yeah, I like that.
Yeah, absolutely.
Another thing that's very good about John is that I can understand what John is saying, like maybe 80–90% of it.
Yes. So I read his papers with respect to the optical parts. I could very much understand what he was saying here with the lasers. But in research that he was discussing recently, I follow that what he's discussing, and he gets similar critics he got from us here now, from other people.
Yeah.
Well, the exact same things, and what exact same, like if you say it's a slit, then the slit is open or not, but a slit of glass is not a slit, but has an aperture, so tell the aperture, tell the calculations, blah, blah, blah. The exact same thing what I would have said. And making an experiment with lasers in front of a fridge is innovative, but needs to be defended in a scientific way.
Okay, yeah. Yeah, I mean, well, I'm talking more broadly about his more cosmological worldview, but yeah, I can understand. The thing is, I can understand his work very easily, whereas, and this is not to put either of you down, Gerd or Christian, like your work is a lot more, certainly Christian's work is very abstract, but the more you're talking about it now, about this border between the eye space, I'm beginning to understand what you're talking about, and it's very cool. Gerd's work is obviously very dense, and there's a lot there, and I think I would need probably another couple of decades to really understand what he's talking about.
That's why it's extremely self-consistent. The eye-space theory has shown that. Eye-space theory would have completely falsified Gerd's work by getting worse numbers.
I'm not saying that Gerd's work is wrong.
Better value, so that there is something to it. What Gerd is doing is more or less looking in the right direction with probably not exact endpoints yet.
Yeah. Well, this is it. I think there's something that Gerd is doing. Like I'm at the moment, I've been discussing with Raja on this new concept of a 4-dimensional universe, and Raja was saying that's like a new paradigm in physics. So it's like really what's the word? You know, it's helpful anyway. It's a helpful feedback. But I'm just thinking about Gerd's research. Then he's talking about as the universe is expanding, like you could have one particle, and then as the universe gets bigger, these line segments and the degrees of freedom increase, so the particles get bigger and bigger. And that's very similar to what I'm coming up with at the moment, but it's coming from a completely different place. But and I think it kind of how does the word? It kind of reinforces what you're saying, Gerd, but it takes it in a slightly different direction or something. So you could have, in the model I have, there is no like singularity per se. The space always existed, but that it just got transformed through a 4-dimensional rotation. So, but a lot of the like all the matter of the universe nearly was all clumped in the center. But then as it begins to expand into an infinite universe, or apparently infinite, it all like those little particles. So just to explain, as the space is expanding, the particles, the degrees of freedom expand. So you get like one particle.
No, but it's not only a particle, it's a wave. And the wave is propagating, and the wavelength is expanding at the same time. That means there's not only an expansion, but also a propagation.
Okay, yeah. So these are the things that I find difficult to understand about your work. But just bear with me, like from a more simplistic point of view. So let's say you have these particles, and like there's a particle here, and then there's another particle over here, and then as the space expands, the degrees increase, so there's more and more particles, but the distance also increases. So
Yes,
like
yes,
two little
yeah.
particles could become two giant suns.
Yeah,
with,
but
does that
if the distance between no, if both particles are in the free fall, then they aren't move with respect to the metric wave field, and the wave count between both particles remains constant, but the wavelength is increasing, but the wave itself at the edge is expanding, so that the space is will become greater and greater, but it's about an CT, I don't know the name, universe, where the
charge?
yes, the great circle,
world line or something.
The radius is expanding with light speed.
Right. Yeah. My version is totally different to yours, I think, but I'm just seeing like a similarity there in terms of expansion and degrees of freedom and the particles getting bigger. So,
but I made some pictures about this, like how the expansion takes place. You must only have a look at the, for example, my topology, and so I don't know the name is. There is a very good explanation.
Well, what I'm going to ask here is, like, let's say you have a particle, obviously that's got a high frequency, and in what I'm talking about here, the particle gets bigger and bigger and could become a star, let's say, or even a galaxy.
Yeah,
maybe.
but it's
a star. Would that then the wavelength would decrease? Would it? Because what's the wavelength of a star? It's got to be. I mean, does it? Can you even calculate that?
The wavelength is it's a four leg field, yes, and there are some vortices, and it's equivalent to the gravitational field, and if there is a celestial body, the body pulls out some of these vortices because Abstand, distance between two vortices is the same like the Planck length, yes, and the greater the celestial body or the mass, the more the vortices are pulled out, and when there is a black hole, then there is or only one vortex inside.
Okay.
Yeah.
So where's the mass then?
Yeah, because the gravitational constant, or not constant, parameter is defined as c to the power of 2 warte mal, was heißt mal?
Times.
10, what?
Times.
Times, yeah. Times the Planck length divided by the Planck mass.
Okay.
You can calculate. It's the same. You will get the same result. It's a gravitational constant or parameter, and it only contains values outside a celestial body.
Right. Well, I mean, I didn't follow a lot of that. That's
You
very
can check
complicated.
it.
Christopher, Rajan, with respect of following up, I think I should put another demonstration and a more simple one, not 2 hours long, maybe just half an hour long, because I'm working on a presentation for reducing the time to show iSpace in a unequivocable way, to say that you would watch that, and beyond any reasonable doubt, you would have to agree, because I would like this checkmate in 42 steps. Yeah?
Great. I'd like to see that.
So this is. I have tried that in person with a couple of my friends, and with my new paper with the 1/6961, which was part of the presentation, and after the historic and the other and the calculation, there were so many things. Actually, would you watch the video of the iSpace presentation a couple of times, it would dawn on you what I'm about. But you're just not used to new geometry. That's the whole problem. You think I'm getting super complicated, but that what I'm doing is as simple as a child would do it. Really, is even simpler.
Okay. So we don't need to overthink it. That's good to know.
Absolutely. Yeah.
One question I have though for you, Christian, you're talking about this. How did you put it? The absolute constant of time, 1/16. Right.
1/6961 is the quantum of time in iSpace IQ unit system.
Okay, so this is the question I have here, because I was referring to it as an absolute. So I'm wondering, in the iSpace universe, like the subspace or 6-dimensional subspace, is it an absolute time then? There's no relative.
Yes, it is a non-movable time because it's discrete. It cannot bend or anything. It is a tick-tock like a digital computer simulated clock.
But you have your quantum of time is not the Planck time, or?
No, it had nothing to do with it. I can calculate the Planck time from quantum of time, and I can show you how many quantum of times are within one Planck time if you wish me to do that.
Okay.
But Planck time is a matter of a relativistic bendable effect, whereas quantum of time is not. Quantum of time is strictly Lego and applies to subspace to form the inner mechanics of constants of nature. But the inner mechanics of constant of nature, as like Gert's current explanation, is based on wave count. So the smallest iSpace wave count you can have is 6. This is 3 waves up and down around one center of such a wave, geometrically. And if you make a continuous sinus-cosinus curve to represent that, then you get the wave count of 6 by sinus-cosinus. And if you go to iSpace theory, you have a pi equal 3, but you still get a 6 up and downs over 1, whereas the 1 is itself massful in iSpace theory. So you have 7 things which could have mass, whereas in a Euclidean circle, you have a 0 size dot, which is massless per definition. It's just a geometry in your brain, where you pick your circle in and pull out and say, this is a circle because I say so. Circles are definitions. You have
your iSpace, does your iSpace model have relativistic contents or not?
Yeah, of course, but not inside subspace. It's a 10-dimensional space-time. It is a normal 4-dimensional space-time and a 6-dimensional subspace-time. And the 6-dimensional subspace-time is actually a 7-dimensional thing, has an extremely precise clock tick, and that clock ticks together with integer pixels give an exact amount of everything. And I mean, everything is mass, energy, momentum, whatever you want is exactly precise up to an infinite number of digits. Now, when you have objects which are based on these subspace elements, and each subspace element is like an electron is part of one subspace. So what is actually happening is not the electron is forming geometrically the space, but the electron is the space. So when I'm right with that ideas which are behind that, then light has a positive charge and a negative charge while propagating with the speed of c in a space-time which is not empty at all, which is ether-based. And as the ether is rotating with the speed of light per cell, and the cell is discretized hexagonal, just like Max Planck showed in his first paper. You have a hexagonal 3-dimensional subspace mesh, and you cannot have a hexagonal 3-dimensional subspace mesh because it is geometrically impossible. So you need a hexagonal 6-dimensional subspace mesh, which is geometrically possible.
Okay.
Otherwise, the gears would do friction on speed of light. Now, inside that medium, which can be seen as an analog compressible thing, because it is compressible, there are rotating cells which are either empty or contain something. And when you move a particle from one cell to the other, it rotates through the glass doors, which rotate with speed of light.
Oh, no, it's not what I'm meaning.
For all leptons, all particles, everything which has mass. But Emmanuel is talking about is a longitudinal wave with an extremely higher speed than that, which is resonating like click-clack balls inside the ether medium itself. And this is what the 1903-1904 paper of Whittaker already completely easily show you with math. You better understand than me. So,
is there a frame of reference in your system?
There's a frame of reference per particle, and each particle contains its own substrate.
No, not for each particle, for the observer.
Yes, it's 10-dimensional. So you have a normal Einsteinian relativistic spectrum as you wish in 3 dimension plus time, and nothing is wrong with that. But what you essentially do is every pixel of that 10-dimensional continuum is contained by a 6-dimensional Calabi-Yau subspace.
You must know my system is overlaid to his model, and the interesting thing is that in my model the frame of reference is
I never fully understood what a frame of reference is actually.
It's produced by the wave angle of the temporal function of the metric wave field.
Look, all fields in whatever mathematical description contain sine and cosine waves and repeat itself. Now, when you make a grid over these repetitions, you get integer pixels of I-space theory, and each of the integer pixels of I-space theory in an assumed medium called ether is just the grid pixels of that ether. So we're talking about the same thing with different mathematical description.
Yes, but I have nothing against your model. But I only say it's an interesting thing that both models are based on a little bit different Grundlagen.
Basis. Get the really interesting basis of your theory and why I haven't crushed it to death already, because I would take the time to crush it to death. Would I be able to? But I'm not able to because it's right to an extent which is frightening to me. Okay. So
there's no contradiction between both. Yes. Yeah.
The problem with your model is it works too well for the math it's using. Okay. Way too well for the math it's using, because I-space works right because I'm not doing anything. I-space is inventing a geometry which is unusual, but invention of geometry is change distance definition. This is a mathematical standard theorem. Anybody can do that and define what a circle is as whatever you want. You can make it square, rectangle, route, main. You define your geometry for your circle. A circle is defined to have different equidistant points around a center point in the most easy human definition I can give. Now, if you do it physical, the time to go from each of these points to each other points is equitime distant. Agreed?
Right. Yeah.
So, and that's it. So when I tell you a jump in a Rubik's Cube from the center cell of the Rubik's Cube to the top cell is 1 time unit, you have to accept that a jump from the center cell to the right top unit, which is the root of 2 farther away optically, is also the time 1t, and not the root of 1 times the root of 2. So it is a perfect circle. And when it's a perfect circle, it works like a perfect circle, and all your physical equations apply to that.
Yeah, that makes sense.
The physical equations are not wrong. They have nothing to do with applying it to the geometry. And by applying pi3 geometry to most simple equation of the electron, which I showed you in the video presentation of mine, gives electron mass to 10 digits. And that is by no means accidental, based on a simple assumption of a ratio of the speed of light in any unit system to a factor I can give in mind. It was the root of 1111130 over pi, Euclidean pi to the power of 3. This is the geometric factor.
No wonder, because the electron mass is a direct measure of the reference system.
Yeah, but you're all playing too much for my taste with the curl and the rod and all these kind of things, which imply that you have a continuum. But you don't have a continuum, so when you do these kind of mathematical things, you're approximating there, and approximating as good as your approximations are. iSpace is approximating nothing. iSpace tells you to the pixel what is.
Yeah, but have you also implemented the expansion?
I'm not responsible for looking over anything 10 to the power of minus 13 meters, if you may. I'm not Albert, okay? I'm more Heisenberg.
Oh, cool. Well, there's a little
one difference.
I have
Spirit does the rest of the universe to himself there.
I tell you how concept of nature works. I don't tell you how the universe works, but that has something to do with each other.
Cool, cool.
Christian,
I think there is it has something to do.
Yeah, of course it has.
Microcosm and macrocosm are...
the way that I was able to do the Hubble constant out of nothing shows that there is an extreme coincidence, pixel perfect, also in macrocosm. Otherwise, it's completely impossible. I mean, if I make the slightest mistake with my initial values 10 to the power of minus 13 meters and expand it to the end of the universe, I end off not 20% off. I end up 10 to the power of 144 something's off. And that is exactly what quantum mechanics is doing, if you remember. The worst calculation ever. Quantum mechanics predicts the energy density of the universe and is 10 to the power of 144 off. And this is why iSpace is right and quantum mechanics in large scale is completely wrong. With respect to Albert, this is another thing. Albert made a big mistake, and I discussed it with Emmanuel even this morning, is that he crushed ether for the sake of having consistency in his special relativity. But special relativity is wrong in some way or another, because special relativity is a mathematical thing and not a physical thing. It has to do with nothing is ever flat. So when you move with the speed of light, you would get a layer of 0 thickness in flight direction. It's obviously nonsense. So the minimum physical something you have is a cube of 3 times 3 times 3, or all your waves would get crushed. In continuum, you might think about these kind of things, but a spaceship running with speed of light, like a photon in flight direction, has 0 forward length on the x-axis. And this is just bullshit.
I mean, don't they have like the Lorentz transform, which has like a certain amount of
yeah, but with speed of light, you get a 0 length forward direction length. So a photon is a photon wave is crushed to 0, and we all know it is not, because we know that there is something called I have to do it in German, I think. What is the German word? The hull of the wave. So sorry, forgot the physical word. It's not the wavelength, but the combined wavelengths over all modes. So it's a wave packet, yeah. And the wave packet has a finite length, and that can be very big. I have even had theories like that from Professor Unziker and others who say the wavelength can be as big as the whole universe.
Yeah, of course. But what about this idea that the length contraction is actually a foreshortening due to a rotation in a 4-dimensional space?
No, forget it. Because the mathematics in iSpace doesn't change when you rotate things. All pixels stay the exact same size from a perspective of the inside.
Well, right. Well, we're not in the inside. We're looking at
if you're outside, is the inside, because it's a Rubik's cube. Then what is a Calabi-Yau space? So now we have to talk about geometry a bit. When you fold a Calabi-Yau space 6-dimensional and forget about time for a moment, you only have insight after that. Do you understand this?
But we are outside the Calabi-Yau space.
No. You may a theoretical Calabi-Yau space 6-dimensional is per definition inside only. Do you understand this?
Oh, right. But we exist in the
forget about what we exist or not. It's just purely mathematics. A Calabi-Yau space is 6-dimensional, and the right side is bound to the left side, the upper side is bound to the lower side, and the fourth side is bound to the back side. But when you bend this, you can bend the Rubik's Cube once, you can bend the Rubik's Cube twice, but when you bend it a third time, you bend the inside of the Rubik's Cube to the outside, and you cannot do that in 3 dimensions.
The thing you're talking about is so infinitesimally small that we just don't see it. Like, we don't have any evidence.
It has the exact same mass in physics than before, but optically 0 size.
Right, well, we don't see it, so when
this is why the theories of quantum mechanics think the electron is a 0 size particle, because it's folding up into itself.
Contract. And it could, if there is a 4-dimensional rotation in some sense, then a large object rotating in a 4-dimensional way will appear for
This is a point in the 4-dimensional space-time. Points cannot rotate. This makes no sense.
No, spacecraft is not a point. Spacecraft traveling at speed
talking about the 6-dimensional Calabi-Yau thing, and the wave is inside that 6-dimensional Calabi-Yau thing. So the electron is an extended object. So what essentially is, what I'm saying is that the Calabi-Yau space extends in space-time to quite a distance, possibly 2 millimeters or more.
Huh? Sorry, I thought they were absolutely tiny, these things. If they're millimeter size, why can't we see them?
The space-time.
Sorry,
okay, you really have to read deeper into all these things. A physical constant is calculated from the inside because its values are only inside. Now we measure outside things in labs, okay? In labs, is only real values are measured, and real values are always outside things, not inside things.
But I thought you said there was no outside to these 6. Or
there is none, but in every point of 4-dimensional space-time, a Calabi-Yau space is embedded. And these Calabi-Yau spaces are...
I'm not arguing that. I'm arguing about... I'm talking about a meso-sized object, a spacecraft.
That consists of a lot of objects. So what you can do is you can compress all these atoms to the size of the smallest one, whatever is the smallest one. And what I'm trying to tell you is, in forward flight direction, the smallest one is a Rubik's Cube with 3 pixels, and not a mathematical dot of 0 length.
Okay, well, it's fine.
No, it's not fine, because when you rotate that thing, it still stays a Rubik's Cube.
Oh, yeah, but it'd be so small we couldn't bloody well see it, could we?
No, of course not, but this is not the point. It goes from a relativistic point that the equation telling you to go to infinity is wrong. It has an end where you cannot go to infinity. There is no infinity.
So that's a clarification I want.
The Calabi-Yau space takes over. This is a fence.
Yeah, I disagree with you.
Look, there are 2 theories, and one is you go in an accelerator and let it run forever, okay? With every rotation of a packet of atoms or electrons or whatever you accelerate magnetically, the thing gets heavier. Agreed?
I disagree.
Every rotation of a packet of electrons or protons in an electron accelerator or proton accelerator gets heavier with every rotation, and you disagree. Really?
No, but if you go to Fermilab, they did the test. They found that there was no increase in mass. So I subscribe to there.
When you accelerate something and hit a target with it, of course it has increased mass.
But they measured it. They found no mass increase.
Right?
Now we're talking either about completely different things. Now look, you have an electron, and I-space theory tells you its rest mass up to the last digit, right? Right or wrong?
Say, I mean,
so you have rest mass in books, yes or no?
Sorry, what?
Do you understand what rest mass means?
I'm not even sure I agree with the term of rest mass, to be honest with you.
Rest mass is what the particle has. Would it have 0 motion? There is nothing in universe which has 0 motion. It has 0 point Zitterbewegung, but aside of that Zitterbewegung, it has near 0 motion when you keep it in a trap. So you take an atom of a choice you want in a panning trap, and it has 0 motion in the magnetic fields, 6-dimensional magnetic fields of the panning trap. And the mass you measure with that thing is exactly that what the single atom has, because it doesn't move. And you can also measure the mass of a single electron. It's not even difficult.
Relativistic mass, that these are just pedagogical terms.
Now, relativistic mass is mass of objects in motion.
Yeah.
And motion increases up to the speed of light, but never reaches the speed of light in accelerators. So when you are accelerating an electron, say 1,000,000 times in a lab, like in Hamburg, the lab, Large Electron Positron Synchrotron, they're very old, much older than the CERN, and has not so high energies, but it's only accelerating charged electrons and positrons, okay? For the sake, it's easier for the argument. Now, once the electron has reached 99.9999995% of the speed of light, this is a 10 or 12-digit number, okay? You can try to accelerate it further, but you will never go with every round. You put the same energy to the particle, so it gets heavier by the same amount every round, every round, every round. And now I tell you, a thought experiment, don't stop that. If you don't stop that, at some point in time, the electron should have the mass of a black hole and swallow us. Just purely theoretical.
Right. Stop. You don't have to explain it, because I calculated this case in my metric universe.
This was a thought experiment. Let me please explain what's the thought
experiment.
No,
I calculated it at page 205.
I believe you, but that is not the point. So the point is important to understand geometrically. There is nothing to calculate. This is something to understand, Gerd. When you have an accelerator and accelerate something close to the speed of light, you cannot increase its speed anymore, because the speed of light is an absolute barrier.
Exactly. This case I calculated exactly.
Heavier and heavier and heavier, and nothing else.
Yes. And you have a look at page 205.
Only one of you, please. Christopher first.
I want a clarification. One of some Christian. When you say Lego, is it LEGO or LEGGO? No. So
Can you repeat the question? You're hard to understand voice-wise. Please repeat.
Okay. Can you? I just tried. It's a mere simple clarification. After that, I want a clarification from Gerd. But Christian, when you say Lego, we mentioned Lego. Is it LEGGO or LEGO?
No, the toy pieces you buy for your children, Lego.
Oh, okay, Lego. Yeah. Because I thought
the bricks.
Sometimes you are referring to the Lego experiment. Okay.
No, I'm not Lego experiment. I'm talking about the toy which children play with.
LIGO. Oh yeah, that's fine. The other one is Gerd. Do you believe in infinite universe? The universe is finite or infinite?
That's a good question. Gerd.
Is the universe
finite? I'm writing. Now you can ask me what?
Great. Thank you.
From your analysis, is the universe finite or infinite?
I did not understand.
Is the universe finite? Is there a boundary? Is there an edge to the universe, or is it finite, or is it infinite?
It's the finite. What is finite?
Is it finite?
Final.
What is the German?
A closed universe is typically finite or assume finite, but it's not finite either. A closed universe is infinite as well.
Moment.
Space universe is closed. So go to the right side, you come from the left side. Go to the upside, you come from the downside.
You mean finite? It's finite, not finite. Finite.
Yeah,
in English.
My English is
finite.
But it appears infinite. It appears infinite.
Yes, it's finite.
In my model,
I have a world radius calculated. The world radius is.
So you're saying there's an edge. There should be an edge. If it is finite,
there's no edge.
No, there is a an edge is I don't know, but at one end is the wave front, and it's particle horizon, and at the other end we are living. It's event horizon. Yes. And,
yeah, but that actually does not imply that there's an edge.
No, from my point of view, Gerd is doing something like what Susskind has suspected, that we're living in a 10-dimensional holographic entity. And when the holographic entity extends, the number of entropy is bigger. We're just a library in the center of an holographic 10-dimensional entity. You have to read the Susskind.
It's projected from the outside.
Yeah.
I agree with that for sure. Yeah, that just
and that fits very well to the data models of everything. So iSpace is a data model theory in all essence.
I don't think you need 10 dimensions necessarily, but
you know, Susskind why 10 dimensions are necessary.
You're talking about like smaller subspaces of that kind of
nature.
No,
Susskind's 10 dimensions are very related to my 10 dimensions, but they are not exactly the same.
I'm pretty sure Susskind's holographic universe projected from that's just 5-dimensional.
I do not need any holographic, and I do not need.
You have to show me your sources on that one.
I have the book. This is good enough.
Yeah, okay, that'll do.
And I've read it twice.
I get 10 minutes, 5 to 10 minutes.
They asked me to publish it, and it is under work, but I don't know when it will be published by the. You know, there was a mail we got.
End of the month, the frontiers, right?
Are you trying to peer review your model? Yeah.
What?
Are you trying to peer review your model at the moment?
It's ready. Yes.
That would be very interesting. Yeah, indeed.
Yeah, that would be. Okay. Well, I also have a model that I'm working on, but it's going to take me forever to get done. But when I get it going, it'd be interesting. I've been asking Rajan to maybe supply some of his more metric, how do you say it, general relativity stuff to it. That would be really interesting. Probably need to work on it a bit by the sense of it, but you have the Legender and other transforms that might work. But then Gerd also, you just got such a wealth of equations, and it would be interesting if they could be applied, but maybe the models are like, I don't think they are as different as they may appear. There's definitely similarities based on, you know, the imputation of the SDS.
Yeah.
And then we both found the great attractor, the great repeller, event horizon, and such. So, and then it's based off of that kind of research. So it's based on inferential hard evidence, if you like. So, but then the model itself could, while maybe not exactly your model, I think your maybe gifts and talents and vision, be interesting if you would just like humor the model and maybe just write a bit about it. If you were to apply your mathematics and thinking to it, and yourself, Christian, I'm not sure if it would apply so much because it's a cosmological model rather than a.
No, the model of Gerd is basically electromagnetic model. This is all where it comes from, by all respect. And
right,
because the gravitation is an electromagnetic based
logical. It's a big scale. It's large scale.
It fits with Gerd's model so well, and it fits also with iSpace model so well, because I'm not looking at models. I'm looking at numerical results for concepts of natures. And normally this is numerology, and you can do that all of day, and you get no real respect from anyone doing that. But concepts of natures have an intrinsic dependency based on the unit system's definition. Like length, time, you can make MLT unit systems simple, like mass, length, time. Or you can make Planck unit systems and define the speed of light to 1. And if you do that, then you can have the square of 1 every day. And what a surprise, you get a 1 after the square of 1 and learn nothing. So only a real unit system with real values calibrate your thinking. So when you have a real number for the unit system, like the SI system enforces, and the CGS system enforces the same, by the way, it's just stupid. The CGS is both CGS unit systems, CGS Planck and CGS, what's the name of the other one? Where you have 1/4 pi epsilon 0 defined a different way. are just nuts unit systems for physicists who don't have a computer. They like these unit systems because on a chalkboard they have some advantages for integration calculation, but that's it about. Normally the SI unit system is heaven sent, is God sent clever, and all the iSpace unit system is doing is removing the kilogram and the coulomb and telling you everything is based on volt, ampere, meter, and second, and nothing else. Now that's
right. Well, the point I'm making is I've got this model, which you don't really deal with models, but so there will be like quantitative data coming out of it. I think if Rajan and Gerd both have a look and maybe do some work on it, I'd have even more quantitative data and of a kind that I wouldn't be able to do myself. And then if that happens in the next year or two or even less, would be great. And then we gather that all together, maybe ship it on to you, and then you can say, yeah, this works, or no, this doesn't work, or if you want to cut in earlier
already about the tetrahedral structures. The only thing you will, in one way or another, if you don't learn iSpace theory first, at least from a matter of understanding, you don't need to believe in this thing, but you should have a matter of understanding of the kind of integer geometry, that everything you calculate on lines and points give you traps for division by zero. And any trap for a division by zero is a bad idea when you do higher math on it.
I know, I'll be grand. Thanks for your concern, though. Well, I don't know. Maybe that'll be a problem for the others.
iSpace theory does away with every problem of division by zero whatsoever. So I cannot have a black hole with zero size. I cannot have a universe because all infinity
division by zero in my model. It's not a problem. Don't worry about it. Okay. Because I have infinite lengths in 4-dimensional space times, or not even space time, just 4D. You can divide over zero in my model. It's not.
We could have an all-day discussion on what a metric is, okay? But that will lead too far. So a typical relativistic metric is much more than just the idea of base geometry.
I'm not really using relativity. Just well, you know, I'm saying it'd be interesting to see how it works within the model, or if it does, or if it changes the results. But my sole interest is just to create this 4-dimensional model of the universe, and then after that, apply the different things and see, does this change the way that we look at the universe?
Yeah, but the interesting thing of the model will be to see if it predicts a natural space-time phase change in 10 to the minus power of 13 meters. And if you don't have anything with the SI system, if you're an extraterrestrial, I would not tell you 10 by the power of 13 meters because you don't know what that is. But I tell you it's the root of the Bohr radius times the root of the classical electron radius. And that is the same for anyone extraterrestrial or terrestrial calculating this number in whatever unit system.
No, I don't think it's going to have any real bearing on that. I think that's a separate issue, assuming that's even correct, but I'm guessing it is based on your work and how accurate it is. But this is more of a different thing, but it does relate, as Gerd was talking about, the very small and the very big, you know, this kind of idea of a holistics thing. So it's more in line with Gerd's work on that front, and I think it could also...
What I'm saying is don't do it with Excel. So you need about 20 digits or more precision to go from the very small to the very big to get meaningful numerical results. You cannot do it with Excel.
Well, you see, the way I'm doing this is different to how your mind would approach it. So I wouldn't worry. It's going to be different. So
I'm curious.
You won't fall into those traps because it just avoids them altogether, because it's just not interested in them because they're too difficult.
I just want to make a comment. The micro, you know, one of the things that the microcosmos and macrocosmos, why I analyzed recently from my formulas and everything, that actually the astrophysics level and the quantum level, only space fields exist. So they can collapse to each other, they can short circuit, and that will make sense why the micro and the macro could be connected. In our level, mesoscopic level, the time fields exist explicitly. It comes out, exists. So that way it's limited. You know, whenever you have time field, it limits a lot of things. That's why we exist. But the space fields, there is no limitation. They can be superluminar or anything, and they can collapse to each other. And so that's why I think you will like Gert's work, microcosmos connecting the Hubble constant, and it works because of that. I think what Christopher is also saying is similar thing. So I think that should not be a problem. I mean that's my
all I'm saying is all the models you make in whatever geometry, whatever kind of abstraction, live within constants of nature. You cannot ignore that.
We'll come back to that. Eventually, you are the final, you will evaluate.
It's not necessary that the model can calculate these, but the model must not do anything which refuses known experiments by constants of nature.
It's a good check. I agree with Christian. It's a good check, the iSpace.
Definitely.
It calibrates ideas. This is what I'm saying.
And it needs to be falsifiable as well. And that's okay. I'm happy to falsify this idea, by the way, as well. It's just fun making them. But if you falsify them, then that's fine. It goes in the bin, kind of.
Same thing that you did with my work. I can move on to the next one.
Exactly. Yeah, and I think it would be very interesting, Rajan, if you consider my idea of
you have to send me more details how to do it.
Oh yeah, well I will obviously, but also like going out there and sort of scraping the web and bringing back some like really interesting.
I agree with you. I also do the same thing. Even though I don't have a background, I catch up and then correct myself. That's how it works. Even for
I mean, if you could like gather info and then do a presentation on like what's going on out there, and I mean, we could all have a go at that. I mean,
Rajan, I sent you the links to this physicist which I showed you the last time, which is from 2004 or 2008 or something, when I was very, very young. It was one of the links I got in my physics study to a Munich professor of mathematics who was teaching quantum mechanics and relativity and all that. And he did that in a way which was unusual. He didn't want to do abstractions. He wanted to go to the bits like an assembly programmer would go, and not try to make abstract curl and rod and differential equation, but said, what does that mean if you calculate with a pocket calculator to 10 digits in detail for every calculation? And what is the physical meaning at that step in detail? And why do we do it? And this paper is only 3 pages long, but is unbelievably wealthy for my brain, because in the beginning I didn't understand anything what these guys were talking about. And after that paper, I found it comparatively simple what they tried to say in a very complicated mathematical language.
Oh yeah, can you send that on? That paper?
Yeah, I sent it around. This is what I promised last time. I showed it you last time, but I didn't.
Send it after that. That was very good. Yeah. So did you send that through ResearchGate or over email?
I sent both, whatever. So I sent it directly by email, and the link to the original page, because they still exist in the internet. The other pages of this professor go to chemistry and everything is also very interesting.
What was that, Rajan?
No, we have to, Christian, you have to send us that paper. Because I have not got that.
Did I post it into the chat? I'm not sure anymore. I thought I wanted to send you that by email.
Yeah, you were meant to. I don't think I got it though. Unless, make sure that you're not replying to a previous email and send it like as a new email, and then we'll be able to see it because your name will be there. But we don't.
Send it new to everyone individually is probably the best.
Yeah, if you send it to everyone, but just make sure that you start a new email, because if you just that would make it easier.
Yeah, we can.
Okay, great guys. I think we'll probably leave it there for today.
Yeah. That's a good idea. We will have next week, Christopher.